Welcome to class number 4, session number 1. The present class will deal with sensors that are based on metal nanoparticles. We will start first by an introduction to the basic properties of the nanoparticles. Nanoparticles are defined as small objects that are sized between 1 and 100 nanometers and that behave as a whole unit with respect to their transport properties. Nanoparticles are size-dependent, and therefore, the properties of the materials change as their size approaches the nanoscale and as the percentage of the atoms at the surface of the material becomes significant. The interesting and sometimes unexpected properties of the nanoparticles are significantly due to the large surface area of the material, which dominates the contributions made by the small bulk of the material. For the sake of comparison, bulk materials, or mainly particles that are large than 1 micrometer in diameter, contain insignificant percentage of atoms on the surface compared to the number of atoms in the bulk of the material. Therefore, they don't exhibit size-dependent changes in their physical properties. The present slides show one example of the unique properties that are related to the size, and this unique property is the color of the nanoparticles. Nanoparticles are often possess unexpected optical properties as they are small enough to confine their electrons and to produce quantum effects. The size-dependent color of the nanoparticles was utilized, though without any intention, by artists as far as the 9th century for generating a glittering effects on surfaces of pots or colors in stained glass. As seen in the presented figure, variation in the size, shape, or type of the nanoparticles have dramatic effect on their colors. For example, spherical gold nanoparticles with diameter of 25 nanometers look green, and gold nanoparticles with 100 nanometer in diameter look orange. On the other hand, spherical gold nanoparticles with 100 nanometer in diameter exhibit orange color at the time similar size of spherical silver nanoparticles exhibit yellow color. Also, one can evidence that spherical silver nanoparticles that have 100 nanometer in diameter exhibit yellow color, and the time silver nanoparticles that have similar characteristic size but a prism shape show and exhibit red color. Several studies have shown the ability to control the nanoparticles type, starting with cores made of pure metal such as gold, silver, nickel, cobalt, platinum, palladium, copper, aluminum, etc., etc. Also, several studies have shown the ability to produce nanoparticles that are made from metal alloys such as combination of gold and silver, gold and copper, gold, silver, and copper, etc., etc., and many examples also can be found in the scientific literature. Of special interest is that the formation of the nanoparticles is relatively simple and to some extent comparable to cooking. In one common wet chemical route, the main ingredients are metal salt, the right solvent, and the appropriate reducing material. What you need to do right now is just to mix them all together and you will have metal nanoparticles. Of course, there are other formation routes for the metal nanoparticles which we will discuss later on in the next sessions. In addition to their size and type, the shape of the nanoparticles can be engineered and controlled. The size of the nanoparticles can be determined by the ratio of the ingredients during the cooking step. Generally, a higher ratio of gold in comparison to the other ingredients will result in larger nanoparticles as seen in the figure presented on the screen in panel number A. By changing other conditions during the synthesis, like the temperature, other shapes can be formed like nanorods, as could be seen in panel number C in the figure. Other modifications can result in more complex gold nanostructures, as could be seen in panels number H to panel number O. The variety of shapes of the nanoparticles have some promising applications. One field is in the biomedical application, where the nanoparticles have desirable optical properties and potentially cargo-holding hollow structure that can use for drug delivery, such as the structure seen in panel number F in the figure presented on the screen. An important aspect in the nanoparticles field is the ability to encapsulate the nanoparticles or to modify their surfaces with a wide variety of molecular ligands, including alkyl thiols, alkane thiolates, arene thiolate, alkyl trimethylsiloxane, dialkyl sulfides, DNA, proteins, sugars, phospholipids, enzymes, and many, many more. The encapsulation or the surface protection of the nanoparticles is extremely important for a number of reasons. The first reason is that the capping ligands can protect the nanoparticles from agglomeration, namely, with no protection of the nanoparticles, these nanoparticles will connect together and form larger particles. That way, the special properties of the nanostructure will be lost. The second reason is that capping ligands allow surface protection that can help achieving specific properties. A simple example is the length of the protecting ligand. By using a longer protecting ligand, the distance between the nanoparticles will be larger, thus affecting the analyte amount that is absorbed between the adjacent nanoparticles in sensing applications. The third reason is a natural continuation of the first two reasons. More specifically, capping ligands allow achieving a hybrid combination of chemical and physical functions, which would have a great effect on the sensitivity and the selectivity of the sensors. Now, we can see that nanoparticles capped with organic ligands can be applied in several forms. One form is to apply the nanoparticle as is, without a linkage between them. The second form relies on creating a highly ordered sheet of nanoparticles by utilizing the protecting ligand as bonder or linker that link between the adjacent nanoparticles. This form of linked nanoparticles is illustrated in the figure seen in the presented slide. Achieving intra-linked nanoparticles involves exchange reactions followed by inter-particle linkages, including thiolate gold bonding, which is seen on the left image, hydrogen bonding of the carboxylic acid terminal groups, which is seen in the right image on the screen, and selective dicarboxylate silver bonding, which can be seen in the middle image on the screen. The nanoparticles are the yellow spheres, and they are covered by two protecting ligands, as could be seen on the screen. One ligand is connected only by one nanoparticle by the sulfide or S bond, which is sulfur, and its length is represented by the letter N on the screen or in the schematics. The other ligand is connected to two different nanoparticles as indicated by the letter X, and the length of these ligands is M, as seen also in the scheme on the image. As could be seen, when N is smaller than m, the nanoparticles matrix will be extremely dense. On the other hand, when m is larger than m, the nanoparticles matrix will be much more flexible. These properties are important when using nanoparticles as devices or sensors, as we will learn later on in this class. The control over the values of n and m generally control over the length and characteristics of the protecting legend will determine the properties of the device based on the nanoparticles. Properties that would be affected by the legend are, for example, the electrical properties like the electrical resistance and the ability to sense different molecules by these devices as well. To summarize the unique features of the molecularly modified nanoparticles for sensing applications, we can mention the following points. The first advantage is the large surface area that is useful for analytes, absorption, or in catalytic processes. The second advantage is the simplicity to synthesize nanoparticles, thus making the fabrication process cost-effective to some extent. The third advantage is the ability to control the size distribution of the nanoparticles, something that would help and will enable low noise levels in potential sensing applications. Metal nanoparticles are soluble in organic solvents, something that assure easy application of solid-state surfaces. Also, metal nanoparticles are stable in air, something that might have promise for long shelf time as well as long life operation time. Also, another advantage is that the legends on the nanoparticles can be exchanged, thus allowing easy engineering of the nanoparticle surface. Additional advantage is that the nanoparticles are very easy for characterization, and that nanoparticles with or without molecular capping legends have a range of interesting electronic and optical properties, most of which can be utilized for sensing applications. We come now to the end of class number 4, session number 1. Thank you.